Okay, so today I'm going to kind of present the results of homework 1. It's kind of interesting to see how everyone did. There was a very wide variety of performance pretty much across the board, but overall it was very, very good. I think you all found out this is a very difficult assignment and it's hard to get good performance on these machines. The best result was about 65% of peak. And I think ACML was somewhere around 85, so that's pretty close. I think they did a combination of just basically SSE, a couple levels of blocking, some padding and transposing the matrix. This was kind of interesting. Three codes. We ran it on a longer benchmark, and 3 codes seg-faulted. And then when we looked at it, it was really because they forgot to free memory. So that it's important to free memory if you're going to run the same code over and over. And one last thing, some groups were benchmarking their code just by running the executable. So be sure that you're actually submitting the job to the compute nodes, because the login nodes actually are about half as powerful as the compute nodes. So we ran some codes, and they went twice as fast as the people have reported in their reports. We also ran some code that ran faster on the login nodes, which is kind of interesting. The takeaway from this assignment, if you didn't notice, was that these math libraries are very efficient and it's very difficult to get this performance. So if you're using a function like matrix multiply, which you expect would be contained in these libraries, you should probably use that. So this is the performance of the entire class. Yeah, numbered by team. So I've color-coded it by how you use the intrinsics. So the compiler may have auto-vectorized. Like I expect group 1 here probably was using SIMD, but they didn't explicitly write it with intrinsics. So the green points are people who used aligned SSE. So that's when they loaded from using the load PD instruction. And the red groups used the load UPD. The black groups kind of did both. So there was one group that did a special case if the matrix was even or odd. So in one case, you could do aligned, in the other case, you couldn't. And the blue groups didn't use intrinsics. And the spike is pretty interesting. That was some code that ran very well if the matrix was close to 64, multiples of 64. But then for the fringe blocks, it didn't handle it as well, so the performance was lower. Oh yeah, sorry. This is so we ran from all n from 1 to 768. So the median is just the median of those and the max. The top line. This is just some more detailed performance. You can kind of get.
It almost looks like simpler is better.
Oh, sorry.
So it seems like people who actually put in more complicated optimizations didn't do as well as people who just did aligned SSE.
Well, so to do aligned SSE, you had to make a couple optimizations so that you could do that. So, so it's actually kind of tricky to use the aligned SSE, because if your matrix is odd, then I think a lot of people found out, then you'll get a seg fault if you try to do a load.
I was just surprised that doing both could possibly be slower than doing one.
I see. So I think the both was just when you would do a special case.
That branch may be
Or just that half the values are using unaligned, so they go slow, or so they go slower, half the matrix. Okay, so you can kind of get some insight from the shapes. Some of them are pretty interesting. There's a difference between smooth curves and ones that go up and down with odd and even, like we were just talking about, because the even cases are easier to handle. This green one is the one that Oh, I'm sorry. So gigaflops is kind of small. Gigaflops performance, so up is good. And then matrix dimension from 1 to 768. Yeah, so these were the best performing, and it kind of goes down from there. So the screen one was very interesting because it was very well optimized for multiples of 64, but then the fringe blocks kind of brought the average down. And if anyone feels like their performance is misrepresented, then let me know, because I ran a lot of these, so they're I tried to use the right compiler and everything. Yeah, the team numbers are written very small on here, but they're on the web page a lot bigger. By the way, this is.
I thought you should have asked them to guess.
Yeah, if anyone sees something interesting a reason, for example, why it does this, and if you have any intuition, then it'd be interesting to hear. All right. Thank you.
Maybe we can announce now. So if you're having trouble finding a group for homework 2, just hang out after class, and we'll figure out who's still looking and put you guys together.
Can people hear me now? Okay, so we're going to have, as I said, a slight change of schedule, and I'll talk about UPC today, and then and you'll be using this in the third homework assignment, and then next week Jim will start talking about dense linear algebra probably, and then we'll go back to the stencils, which was structured grid topic, which will get filled in. So why are we even talking about another programming model or programming language than MPI? The basic problem is that if you try to run an MPI application on every one of your cores, which is the typical way, so about 90% of the NERSC users program the machines that way, even though there's multi-core nodes in there, they run an MPI process per core. And we saw some of the problems with that last time. I talked about adding OpenMP threads, and certainly that it shrinks your memory footprint if you use more OpenMP and less MPI, because you've got to chop up your problem to use an MPI process, and you can share the data when you're using an OpenMP process. So the general question, though, is, do we have to really write 2 parallel programs now? Is there something that we could do that would allow us to program both using the shared memory and also allow us to run on a network? So the typical problem has been, if you try to program in OpenMP, you can't really run the code on anything other than shared memory hardware. There has been a little bit of research trying to take OpenMP applications and scale them up to run on clusters, but it's not really something that you can use in general yet. So there's a few benchmark cases where people have been able to get that to run. On the other hand, you're kind of wasting your memory if you're using MPI all the way down in the cores. So the idea of these partition global address space languages, or what are called PGAS languages, of which UPC is an example, is that it gives you kind of the best of both worlds. So it gives you a global address space like OpenMP. What that means is that you can access memory anywhere in the system by doing a read or write operation without involving the process on the other side. So you don't have to say receive. So in MPI, you always have to say receive for any send. And in one of these PGAS languages, you could just read and write memory locations. So this is kind of a cartoon of what the memory looks like. There's, first of all, with each thread, there's a private part of the memory. So you can think of this, and by default, it's going to be the variables that are declared inside of your functions are going to sit inside of each of these private pieces of the memory that's associated with each one of your processes or threads. And then there's a shared part of the space where you can have, where any thread or any process can see the data structures that live in the shared part of the space no matter where they live. Now, if you just had this yellow part without these little dashed lines, that would be a global address space, and that's really what you have in a shared memory hardware system or an OpenMP or something like that. But what makes a PGAS language a little bit different than OpenMP is that it's also partitioned. So although you can access anything in there, there's a way that you can tell in the program whether or not something lives locally, that is is physically located in your local memory, or is something that's remote. And it's drawn here, it's a little bit subtle, but with the width of the pointers. So there's skinny pointers that can only point within your kind of physical address space. So think of this as a UPC program just running on a cluster with one processor on each node and a network between them. Well, a local pointer is just a regular memory address. You can load and store that. A global pointer, one of these G things, is a wider pointer. And inside that pointer, for example, in the implementation, it may contain a thread ID, which says which processor the data structure lives on, and also its address, where it lives in memory. Okay, so that just give you a little idea of how you can implement it. It actually turns out that some of the early versions of these languages came out of class projects, not unlike some of the things you're going to do in here, where we were trying to figure out whether you could build this kind of illusion of a global address space without having any kind of shared memory hardware support underneath it. So there's a few of these languages that are kind of the old, more mature PGAS languages. UPC, CoRE Fortran. A version of CoRE Fortran is actually in the Fortran 2008 spec. So there's pieces of CoRE Fortran that should be coming out in every Fortran compiler. Titanium is a language we developed here. I'll give one example of that at the end, just to say a little bit more about an application written in Titanium, but it is a global address-based language based on Java. And in these three languages, we say they don't virtualize the processors because as an MPI, and unlike OpenMP, an MPI, as I said, there's a fixed number of processors at the beginning of the program. You basically have the same model where the main function, think of it as being copied, one copy of it per core. And it's going to run that way. Now, as I described this, that you could imagine running this, mapping this onto a cluster architecture, but you can also map it onto shared memory architectures. And in that case, if the whole thing were a big shared memory architecture, then although these lines are here in the programming model, in the sense that you can ask whether some data structure lives locally or not, in terms of the physical implementation, they may be all sitting in the same address space. You can also run this on then a cluster of shared memory machines where some of these little lines are more important than others. And there's sort of future work trying to figure out exactly how to take advantage, what is the best language support for allowing you to write algorithms that optimize for that. But the basic idea is you can use the same programming model across both shared and distributed memory. Yes?
And where do the languages at the bottom?
Oh, right. So, sorry, yes, I went forward. So the languages at the bottom, X10, Chapel, and Fortress, were three languages that were developed over the last 5 years or so from a DARPA project called the HPCS program. X10 is from IBM, Chapel is from Cray, and Fortress is from Sun. And I think Fortress, as far as I know, is not so active anymore, but X10 and Chapel are still active projects. They are both, X10 was originally based on Java. It's changed now. I think they've got another language implementation. Chapel is its own language. It's not really based on another one. Fortress was also its own. So they take the idea of the global address space or the partitioned global address space as in these other languages, but they don't have this. They do allow you to create threads more dynamically, so you can invoke work, you can call methods remotely on objects that live in other parts of the address space, which creates some work that has to be done remotely. So they have a different sort of model, execution model that's a little bit more general than what's in the older languages.
How does it compare to like when they use shared virtual memory for distributed?
Right.
Like
Yeah, so the question was about what about shared virtual? How does this compare to something like shared virtual memory? So there was a whole set, big set of papers that were in the early, mid-90s maybe, on distributed shared memory systems, DSM systems, both sometimes with hardware support, but also with just purely with software support. And the key difference between them is inside the PGAS language, because the locality model is built in the implementations, we never cache remote data. Okay, so that's sort of the key difference, which makes it, if you think back to the lecture on cache coherence, right, what makes it really hard to build a shared memory machine is you got to figure out how to keep the caches consistent. So if you never cache remote data, You only have to worry about the copy that's in memory and the copy that's in the cache, and the hardware does that for you. There's one other little trick you have to worry about if you're building hardware for this, which is if you're going to do remote reads and writes from the network, you need to make sure that the network sees the up-to-date values. But it's much easier than keeping the entire set of caches across a very large system coherent. So that's really the key difference. And so those DSM systems tried to give you really more of a cache coherent, a uniform memory access model, whereas this is very explicitly a non-uniform or NUMA memory access model. Good question. Any other high-level questions? Okay. So let's see. I'm going to talk a little bit about give you an overview of UPC. So I'll talk a little bit about the background. So as I said, it came from influenced by both message passing, which had the advantages that it scaled well on clusters, and then shared memory machines, which was that it kind of worked well. In truth, this language, UPC in particular, was really motivated by a group of people who were writing large-scale parallel applications that were doing various kinds of understanding very large, complex data sets. So these are people at the NSA. Okay, so it's about all I can tell you about what they do, except that their favorite benchmark, the only one that we know about, is something called GUPS, which is random accesses across memory. Literally, you're reading in a stream of addresses, and you're trying to access memory. So you can see in that kind of a program, you can think about computing a histogram as something similar. So you've got this big stream of indices, and you've got a histogram that's spread out over your machine. How do you program that in MPI? Well, it's very awkward because you get an index and it says, well, this goes on a bucket that's on that other processor, but how do I get that processor to say receive when it doesn't know that I own an index that it has? And so it's not a very natural way. You can program it in MPI, and you end up using wildcards and things like that, and taking in messages that come from anybody and then processing them, but it doesn't really fit very well. So these global address-based languages were also motivated by random access problems. Questions that are of interest now are things like some of the graph problems that come up in computational biology and bioinformatics. Would these work well in a partition global address-based language? Or some of the problems that we'll see when we get to sparse matrices. The sparse matrix, kind of the main part of the computation itself, tends to work well in most of these programming models that we've seen. But when you have a graph problem where it's really irregular, they may be more well-suited to one of these PGAS languages. But actually, at the moment, the biggest interest in PGAS languages is coming from multi-core nodes that are on these large-scale machines and the desire to shrink memory, and the concern that OpenMP does not give you locality control. And as we saw on the Hopper machine, even though it's got shared memory, it's also it's got some very NUMA-like characteristics, and so the PGAS model gives you some ability to control locality. Okay, just a brief history of it. There were a few languages, so kind of like MPI, there was some experience with these things before we sat down to do the UPC language spec, which was in 1996. I hate to say, but and it was based on a language that David Culler and I had developed here called called Split C. There was another language that came out of IDA, which is a research organization that works with the NSA, and that language is called AC. And then there was a language called Livermore, which unfortunately was called PCP. There's now a consortium of people that control the spec for the language, and so there's a community effort around this language. It's not just a Berkeley project. The design goals of the language were to get high performance, expressiveness, by which I mean kind of expressiveness of random access, kind of irregular programs, and to be consistent with the underlying goals in C, that is the underlying design of C, to not put in things that are inconsistent with C, and portability. UPC today, there's a bunch of different vendor compilers, so if you go out and if you look at a lot of the machine procurements at places like NERSC, they will require a UPC compiler and in some cases a CoArray Fortran compiler. So there are not as many CoArray Fortran compilers yet, but I think that will change because of the inclusion of some of the parts of CoArray Fortran in the spec. So there's compilers from those companies. There's also a GCC implementation that you could download and run on any Unix machine at least, and the Berkeley UPC compiler, which actually certainly runs on a Mac OS environment, and also runs on a Windows environment. I think if you're running Cygwin, that's always our most difficult port, but I believe that one is still working. So you can run it on your laptop as well as on a large-scale machine. So there's kind of a pseudo standard also in the C sense of a standard, because the UPC extensions have moved into the moving into the GCC trunk. So in the C context, we've talked to the ISO-C committee, but it's really hard to move things into that standard so far. Basically, there was a meeting where we talked about programming models. The ISO committee talked about how to add parallelism extensions to C, and after people talked a little bit about some of the different models, the committee decided that they didn't understand enough about parallel computing to decide what to put in the language, so they kind of decided to wait and watch what was going to happen. But kind of a first step in standardizing things in C, you get kind of a pseudo-standard by having it in GCC. So it is in the GCC main trunk, which makes it more, I think it's going to be around for a while. And things become kind of like a standard once they're in there. So it's also, and as I mentioned before, really some of the bigger applications are things that we don't really know very much about because they're these irregular kind of graph problems. Okay. What's the execution model look like? Very familiar to, though now that, since you've seen MPI, hopefully that's kind of ingrained in your mind. We have the idea of threads. There's a little confusion. Normally you use the word thread when you're talking about shared memory and you use the word process when you're talking about distributed memory. Because UPC is kind of in between because it's kind of got this logical partition, even though you can see anything remotely. In UPC, it's called threads. In some other of these PGAS languages, it's called processes. But anyway, so you can ask for how many threads there are. You can ask for what your thread ID is. Remember, just think the main function is running it from the beginning on each thread, and each process. And there are things like UPC barrier you can use to do global synchronization. There are other kinds of synchronization I'll talk about later. There's also a kind of a parallel loop construct that I'll talk about as well, but you don't really need that to write an interesting UPC program because the program is fundamentally parallel as soon as you enter the main function. There's a couple of different compilation modes that it's important to understand because if you write, because it changes somewhat the semantics of this pseudo-variable threads. So threads tells you how many threads there are in the world, and just in any C program, in the C language, there are places that you can use a compile time constant that you can't use another variable that's not a compile time constant. That is something that is known at compile time. And threads, for example, if you want to put it in as an array, the trailing array dimension of an array, in something that you just declare in place, so not dynamically allocated but statically allocated array, then you can only do that if threads is something that's a compile time constant. So in the implementations, you can compile things either in static mode or in dynamic mode. Normally, it's convenient to compile things in dynamic mode because it means you can run it on any number of processors once you've compiled the program. But there may be some optimizations also that you get in static mode. So here's the simplest UPC program. So first of all, any legal C program is a legal UPC program. There are times when that makes it, that cause some difficulties for the standards committee because there's things that you would kind of like to throw out of C sometimes, but especially in a parallel environment. But anyway, that is the rule. And you can compile it and run it as a UPC program, and what will happen is you'll just get P copies of the thing running, and they'll do redundant work, whatever the problem is that they're doing. So, but if you want to write a slightly less trivial program, here's the hello world example, which is just using those two pseudo variables, mythread and threads. So a slightly more interesting example that I'll use, a little bit different than the pi example. Pi is yes. Oh, what did the last example do? So the last example would have each thread would print out thread my ID of the total number of threads in here, and then the hello world from that. Hello world after that. So exactly what behavior you get in terms of how those are interleaved, it depends a little bit on the runtime system. So there's a question that comes up is whether when you do a printf in a parallel program, are you guaranteed that that printf will be kind of completely printed out in one whole statement? You certainly do not have any guarantee of the order. So this is not going to print out thread 0, from out of four, thread 1, out of 4, thread 2, out of 4, and thread 3. It'll come out in any order, and that's going to be your typical behavior. There's nothing in this program, though, that guarantees that you also won't see the characters kind of mixed together between different printf statements, but that will depend on the implementation of the underlying library. Okay, so a slightly more interesting example. We're going to approximate pi, once again, by looking at the area of the quadrant of the unit square. But we're going to do this now by using more of a Monte Carlo idea, which is we'll throw random darts at it, and we'll figure out what the fraction of darts are that are inside there versus outside the unit square, and then we use that to estimate the value of pi. So first of all, here's just a plain old C program. This now has, if you run this as a UPC program, it'll have P processors all doing the same thing together, but they're not actually coordinating at all. The only thing that's a little different is I'll use a different random number generator in here. So this is let's see, the main function. There's nothing particularly interesting, but as I said, it's already parallel at the beginning, and we're just going to check. This is just getting some, if you don't recognize the C syntax, this is just getting some arguments from the user about how many trials, how many darts are you going to throw. Then you seed a random number generator, and then you calculate you call a function called hit, which calls the random number, gets the random numbers out and looks to see whether they're inside or outside of the unit circle, and then you divide that by the total number of trials and multiply by 4 to get pi. So there's some code missing there from hits, which is on the next slide that I won't really talk about, but is just doing the obvious calculation in there. So this is now p-independent calculations of pi. You may get slightly different answers because you seeded the random number generator with a different value, but that's the only reason you'll get different numbers out. Any questions? Okay. Oh, I should have done my highlights. Okay, so there's the helper code in case you wanted to see it. There's a little bit of stuff you do have to include, upc.h, for example, at the top of the file, and the math stuff to get the random number generator and so on. And then there's just the thing that's calculating x squared plus y squared, checking to see whether it's inside the circle. Okay, so not a particularly interesting parallel program yet. To get something interesting, in this programming model, we have to do some kind of communication. And because it's a global address-based model, we'll do communication by reading or writing to shared variables. We also will have some other kinds of communication, not send and receive, but other kinds of collective communication that will come up. But the first thing that we'll do is just to use the shared variable mechanism to do communication. And the easiest way to do it, albeit not a great thing to do for a couple of reasons, is to just have one shared variable in the program called hours. And that is going to always show up on thread 0, and it's part of it'll be in the shared part of the address space, so the yellow part, so any other thread can see the hours variable, but it is, there's only one copy of it. And in contrast, if you just have a regular variable, the mine variable has a copy in each one of the threads. So shared variables cannot have a dynamic lifetime. So what that means is you can't have a declaration like this inside of a function that's other than the main function. You can have them at the global scope outside of main, or you can have them in the main function, but you can't have them in a dynamic context because they're a dynamic lifetime. Anybody explain why? Idea? Well, yes.
It's on the stack, and then if it disappears, the other threads maybe like trying to point to number that's been since overwritten by something else.
That's right. It's a particularly nasty kind of you can call it a race condition or something, where you've got a variable it's in the program stack, which is the part of the data structure that holds all the variables inside of a function in the implementation when you call a function. So a function has been called and it's running on one of the threads, and another thread calls the same function and then calls it a different function, tries to access that variable, but the first one returns and the variable is gone. So it'll then just be accessing who knows what memory and overwriting it or whatever. And I'll say that these kind of simple shared scalar variables like the R's variable are very unusual in real UPC programs. They're used very rarely except for constants, but it's sort of it's easier to kind of start with this in terms of understanding how the address space works. So here's a program that somebody you might try to write to calculate pi. We're going to use a shared variable called hits. And we're first of all going to divide up the input argument, which told us how many trials to do, and divide that by the number of threads. And then we're going to write this loop that is doing hits, but it's only going up to the total number of my trials. So you should be getting roughly a factor of p speed up because they're all going to work independently on this part of it. You then have a barrier, and then just one of the threads is going to print out the answer. Okay. So what's the problem with this program? Brian.
Two problems. One is you're accumulating the hits in parallel, and that operation probably isn't going to get times. And while
I'll repeat it. Yeah.
So while you're updating, someone else will be updating, so you read off the right housing and things like that. Secondly, everyone's hitting this parallel shared variable constantly on every trial. So it's going to perform like crap.
Right. Okay. So, right. So the two problems are, well, the first problem is that it's going to run slowly. The second problem is that, or the first problem is going to get the wrong answer. The second problem is going to run slowly, getting the wrong answer. So it's not a very good parallel program by any measure. And the problem is because you're doing this update, you actually have a read of hits in this plus equal and then a write of hits. So this is a race condition in the program. Remember what happens is that variable gets read out of memory someplace, maybe all the way across the network of your system. You go and get the variable, comes back, it goes into a register, you increment it there and you write it back. Two processors that are doing that at the same time, you're very likely to lose one of their updates because, say, they both read 0, they both add 1, they both write it back, and you get 1 instead of getting 2. So it's not what's called an atomic operation, and so you don't get the right answer. And in fact, it's basically there's very little computation in this program, so the other problem is you're spending a lot of your time sending messages all the way across the network, and all the processors are sending them messages to thread 0 in the underlying implementation, even though you don't see the send receive here. So all that network traffic is going across the network and probably congesting thread 0 very badly. So it kind of has the right idea. We can fix it in a couple of different ways. One of the ways to fix it is by using some arrays. And this now gets into a programming style that's a little bit more typical of a UPC program, which is to use a shared array rather than use a shared scalar variable. As I said, shared scalar variables like hits are pretty unusual because of this problem that everybody's going to try to access the variable at once. If it's a compile time constant, the compiler will do the right thing with it. But otherwise, you don't really want to use those kind of variables very much. So if we have an array, as soon as we say that an array is shared, what that means is it's going to be mapped across the yellow part of the shared address space. So in these examples here, we have 3 different declarations of 3 different shared arrays, and we're mapping them cyclically. So I think when we do dense linear algebra, we'll talk more about what the different kinds of mappings are. But this is a cyclic mapping, which means each thread gets one element, and then you just keep wrapping around. So in the case, this is an example shown with 4 threads here, and what's in red is the set of elements that thread 0 owns. So it owns the first element in all of the examples. And then for the larger arrays, it owns every 4th element after that. OK, and notice that you can get an uneven distribution there at the end with Z. It doesn't divide evenly, but the declaration still works fine, and the program still works fine with that kind of an array. OK, so how can we use this in the pi example? Well, we'll do the accumulations in a shared array, and this will avoid the race conditions and avoid the problem of clobbering of all the traffic going back to thread 0. So we declare all hits as an array of size threads. This is, by the way, one of those declarations I mentioned before that is going to depend. You can only do this in static threads mode because the compiler needs to know how big threads is. We'll see dynamic ways of doing this a little bit later, but this is a simpler way to write it for now. And now when we do the increments, we're doing it only into the location that is sitting locally on your own thread within that array. You do the barrier to make sure everybody's finished with that. And then my thread will go through and run through the array and add up all of the results that everybody else has gotten for the hits. And it will do the final pi calculation on its own. OK, so this program now works correctly, and it should be much more scalable than the previous one. There's one thing that still bothers me a little bit about scalability of this program. What is that? It might bother you. Yes?
Number of threads is really big, and that for loop can get really long.
That's right, yeah. So this last loop down here, it's only thread 0 is executing. It's got a big loop in there, and it's going to run. It could be a serial bottleneck in your program, and if you've got 10,000 threads, it'll take a long time. So we've seen algorithms, we've seen collective operations and things like that. That'll be the idea for making something like this go faster. We don't want to do it serially, but it works to do it that way. It's just probably not very scalable. OK. So the next thing I'll talk about is synchronization. So far, all you've seen is the barrier operation. Barriers in UPC are actually a little bit interesting. They have a split phase barrier. And what that means is that you can separate the notification from the wait on the barrier. So remember, what a barrier basically is saying in the program is, I'm done with all my work as a thread, and I want to wait for everybody else to be done with all of their work. So you can separate those two things in some programs. You can say, well, I'm done with all my work that anybody else cares about, so I'll notify them that I'm ready for the barrier. I'll now go off and do some other computation that's unrelated to the stuff that everybody else needs, and then I'll do a wait when I really care about everybody else having finished the first part of their work. So we just split it with UPC notify and UPC wait. It's also the case that you can use labels on your barriers, which is just kind of a programming convenience. We had thought originally when these were put in the language, we would use them a lot more for compiler optimizations. I think they use it a little bit in some compilers, but they haven't proved to be quite as useful as we had thought they would be. They're just integers, and you know, good programming practice means you make up a mnemonic name for them, and you say, well, this is the barrier that's inside of merge. And it's useful in a little program example like this because you've got a barrier in which some of the threads are going to be at this textual instance, and some of the threads are going to be at this textual instance. So it just helps you kind of make the program more readable. Okay, so barriers are, they're a little interesting, as I said, because of the split phase nature of them. But UPC also has locks because of the fact that it has shared variables. You often want to lock a shared data structure because you don't really know at what point different threads are going to access it. So this is going to give you mutual exclusion. It doesn't force anything to happen in a particular order. It just says no two threads can be accessing something at the same time, just as we saw in pthreads and in OpenMP. So locks in UPC are what are called an opaque type in programming languages, which means we don't really get to know what's inside of the implementation of a lock, and we shouldn't really care. So there's just a UPC lock T type, which is the type of any variable that you allocate that you want to be a lock. And so you have to you can allocate a lock both before you use it. You have to allocate it, and so you can have a lock in which every thread gets kind of a pointer to that lock, or you can allocate one in which that just one thread gets a pointer back, and it may hand that. Presumably, it's going to hand that pointer out to at least one other thread. Otherwise, it probably didn't need to have a lock in the first place. So then, when you use it, you just have a lock and unlock statements that are taking in the pointer value, and then you free it up when you're done. So here's a little bit of an example fixing the original version of the HITS code, which still has the second problem that we talked about before, which is bad performance, but it gets rid of the race condition. So this is now a correctly performing bad parallel implementation. But just to show how locks were used in this example, there's an allocation of the lock, and then we just one of the things we do in terms of the scalability to make it a little bit better is we still do a local update of the hit values, and then each thread will do one atomic update of the shared hits value, and that shared hits value then is protected by a lock. And so this is non-scalable in the same sense that the one with the one loop at thread 0 doing something at the bottom is non-scalable, probably even a little bit slower, because what you're doing is to acquire the lock, you go across the network and acquire it, then you increment, and then you release the lock, which goes across the network again, whereas in the case of the one thread going through at the bottom, after everybody else had computed through the array, then there's just sort of one network round trip for every processor, from processor 0 to every other processor. This has got multiple round trips in it. But in any case, it does work. And there are much more interesting examples for which this is exactly what you want to do. Jim?
What if not every thread does that allocation?
It is a... if not every thread does that particular allocate, the program should hang at that point, because this is a collective call. So the UPC all alloc is a collective call. I believe it will hang. It is undefined in the language spec, and I would have to run it to see whether it will actually hang or it will. I don't know that there's a applied barrier inside of the all alloc statement. So it won't do anything useful. That's for sure. Okay. So let's see, private versus shared variables. We've seen a bunch of different things in the program examples so far. So here was our, we have a private scalar variable like the my hits, which was down here in the previous example. Then we had the shared scalar variable like hits, which was the thing you were actually all accumulating into, and then a shared array, which was in the array version. That's all hits, in which each one of the threads gets a different element from the array. And then the lock actually is also sitting on thread 0, just to be aware of that. And it is, there's only one instance of that lock, of course, because otherwise it wouldn't work very well as a lock if everybody was locking different locks. Okay, so what about doing something with collectives? So collectives are kind of an interesting case, there's actually been debate within the UPC language kind of design community about whether collectives should be in the language, because to some people they seem too much like MPI and message passing, but to others of us it's really like data parallel programming, where and this global address space is actually a very natural model that you'd get in a data parallel language as well. So there is a collectives interface. It is currently a topic of still quite a bit of debate. In fact, there's a new proposal coming out of Berkeley Lab and IBM about a new way to do the collectives, because people aren't so they're not so happy with the way the collectives look like right now. So they look a lot like MPI collectives. So I won't go into a lot of details here. It contains kind of typical data movement things like being able to broadcast, scatter, and gather, modeled very much after the MPI collective spec. And there's computational ones like reductions and prefix, which is the scan version. Now, what is a little bit different about UPC collectives, and one of the sort of sore points in the community, is what are called synchronization modes. So if you think back to the barrier example, it probably gives you some intuition about why these were put in here. That we wanted to allow split phase operations to happen. When you call a collective operation, the person that's implementing the collective call needs to know something about whether all the threads are there at the same time or not, because can they go and use a data structure, for example, that they've set up ahead of time for all collective operations? Can they be guaranteed that all of the other threads are in the middle of the same broadcast operation, or the same, which would allow, for example, one thread to just go and write into remote memory? Or could it be that some threads are actually off doing something else and haven't yet hit the collective call? So one of the ways you can avoid this problem is just say, in the implementation of the collectives, is put a barrier at the beginning, put a barrier at the end. Everybody will be, it'll be completely clear that every thread is at the same point in the program, and it will make it easier to implement the collective operations. But that slows things down a lot, to have two barriers every time you do a collective. And in fact, in the spirit of kind of high performance and also trying to overlap communication with computation and kind of relax all these synchronization points, which are also kind of themes within UPC, we didn't want to force barrier synchronization where it wasn't necessary. So so instead, there's different modes that basically say whether or not you're guaranteed that all the threads are together at that point when they're calling the collective, and whether they're all exiting the collective at the same time. That gives you lots of different combinations of interfaces. So, and the other thing just to keep in mind is that the data that you're collecting on, so what you want to do in UPC is say something like, here's a pointer to an array, do a sum reduction on everything that's in the array, even though some processors will have 100 elements and some may have 101 elements, but the implementation of that reduction operation should take care of both the local computation and the coordination of that computation. But that array can have another thread that's reading or writing into it at the time you're doing a collective, and that also complicates the semantics. So that's why there are these different synchronization modes. If you're not doing collective operations on aggregate data structures, on things like arrays, if you're just doing it on scalar values like ints or doubles, you can use what we call the value-based collectives. These were actually collectives that were that we made up a few years ago specifically for CS267, because it was so hard to give this lecture if I had to talk about the general purpose ones, and we found that these value-based collectives are actually good enough for a lot of examples. So here's the Pi example written with a collective. And the value-based collectives are actually in the Berkeley UPC extensions. We should really take the B off of them, because so BUPC things are anything that's in the Berkeley language implementation that's not yet in the language spec, main language spec, that are available from our compiler. These are implemented on top of UPC, so there's nothing really compiler-specific about them. But anyway, so what are we doing? Well, we've collected locally your local hit list, and then you're going to do the reduction across machines. Across the processor in order to get a single value out. So this is just a call to all reduce. It says I want to do an add operation, and the value is going to go back to thread 0, and I'm putting in my hits as the value that's going to be reduced, and it's being done on integers. And so that's what the call looks like. Any questions? I won't read through this, but there's lots of other collective operations. This gives you the format, this extension for all the value-based collectives, and there's also non-value-based ones that are underneath this that allow you to do the more general thing where you want to pass in, for example, an array and broadcast an array. And that's a little bit more about these sync flags, but I gave you kind of an intuition before about the sync flags, so I don't think I want to talk in detail about the sync flags. I will just say that in the more general collectives, there is a default value, which is if you just leave, if you make the sync flag 0, usually the right thing will happen if you're not trying to do something fancy in terms of overlap or optimizations. But you can also control that more if you want to. Okay, so that's the kind of the basic mechanisms for sharing variables, for doing, for getting things off the ground. So in a partition global address-based language, one of the questions is how do you create any shared state? And you can do that with collectives. That's a pretty typical way to do that. In UPC, you can also do it by having a globally scoped shared variable like a shared array, like the all hits array, or you can do it by broadcasting something. Those are basically the 2 ways of doing that. So how are we going to distribute work? I mentioned before that there's a parallel loop. Well, so far we've just been using the fact that the main function is running with different thread ID as the only mechanism to divide up the work across the different threads, so that they have a different mythread value. But there is a looping construct that can make it a little bit more convenient to write these kinds of write some programs, especially array-based programs, and that is using what's called the UPC for all. So this is to motivate that. Here's a simple program to just add up 2 vectors and put the result in a 3rd vector. These are all 3 are declared as shared arrays, and they're going to have the same alignment. So they're all cyclically lined up, which means that V1 sub 0, V2 sub 0, and sum sub 0 are all going to live on thread 0. So that's explicitly given to you in the language definition that they're associated with thread 0. And so we can have a loop then that just goes through and adds up all of the values. This is kind of a cumbersome way of writing only do the sums if I happen to own the values. So rather than having all the threads redundantly calculate the values in sum, which would have a lot of extra work, each thread is just going to add up the values that happen to live on their own thread. And so the kind of general condition is if my thread is equal to I mod the number of threads, then those are the ones that'll pick up the ones that I own. And that pattern of writing this kind of a conditional here is so common that it gets encoded into a UPC language construct called UPC for all. So UPC for all just looks like a like a C4 statement, except that it's spelled differently. And it has the initialization, the test, and the loop, which are just like the C looping construct. And it has a 4th argument called affinity, which is a statement that says that has a value associated with it, and that depending on whether that value, if that value is equal to my thread, then that particular statement will get executed that time. So you could think of it as every thread runs the loop, kind of the loop header, and every time it does that test to see whether or not my threads is equal to I mod threads. So, there are different things that you can put in the affinity statement here. You can put in an integer, and if you put in an integer, then what gets put into the conditional is if the affinity modulo of the thread, the total number of threads is equal to my thread, then execute the statement. Otherwise, don't execute the statement. If you put in a pointer, it asks, there's a underlying call called UPC thread of, which says if it's a pointer, ask the runtime system where that pointer points. And if it points to my thread, then I'll go ahead and execute that loop body. Otherwise, I'll skip that loop body and go on and see if I own the next pointer that's in there. So there's the 2 cases are putting in an integer and putting in a pointer there. So you could imagine, so here's an example. If you put in an integer, though, in both cases, you could write those with these kind of conditional statements, and this is the case for I. So the example that we had in the previous slide, you could, if you just took this and turned it into the pointer version, where you've got a P over there, it's going to just ask if the UPC thread of is equal to my thread in the conditional. Okay, so that gives you the basic idea of the looping construct, and let's see, so what is also going to add is that the compilers can do a better optimization than this. So if you've got 10,000 threads, you don't really want every thread going through 10 million different things in order to get out the 1,000 that they're going to have to actually execute. And so if you've got a simple kind of UPC for all loop, one of the UPC compilers, at least most of the UPC compilers, will turn that into a simpler loop that just does the it just starts at the thread ID that you're at. It just increments by threads each time. So you're only going to execute the number of loop iterations that you need to in order to do the work that you actually have to perform. So it has to be pretty simple expressions. Otherwise, the C compilers, the UPC compilers, can get confused. But that's the basic idea. OK, so there's the vector add example with UPC for all. You can see it gets cleaned up a little bit because you've left out that conditional and instead just put in the UPC for all statement. You could also put in the pointer if you wanted to for the affinity statement. So an example that might be appealing to C programmers is you can put ampersand sum sub I in place of I as the affinity statement that says, give me a pointer that points to sum sub I, the ith element of sum, and then tell me what the address of that is. And then because it appears in this place in the UPC for all, it says, what is the thread that owns the thing that thing points to, which is, by the way, the thread that owns sum sub I. And so you'll get the same results out as if you had put in I. But you could see that hopefully that you could use this for something like a linked list. So imagine you have a linked list or a tree that is represented up in the shared memory. And as you run through that linked list, at each step, you could check and see whether or not you own that particular link in the linked list. And if you do some computation. Otherwise, you would just keep following the pointers down. So all the threads would have to do would have to follow through on the pointers, but only the ones that own something would actually do execute the body where they own one of the nodes in the linked list. OK, so I've shown a couple of examples with really simple distributed arrays. You can actually do somewhat more interesting things with arrays by using different kinds of layouts. This is a part of the language that I find to be a little bit frustrating, mostly because C is not actually a very good language for writing programs with multidimensional arrays. And UPC, because it's consistent with C, is not all that great at it either. But you often do want to do things that are a little bit simpler than a cyclic layout of an array in UPC. So here's a vector addition example where rather than having every processor own every pth element of the array, we'll just store it by blocks. And so all we have to do is in the declaration of the arrays, we put in this little thing that says store it in a blocked fashion as opposed to storing it in a cyclic fashion, which was the default. And what it'll do is evenly divide up the array as much as it can. It'll do something reasonable if the total number of elements in the array is not divisible by the number of threads. And then when you run through this loop, by putting the ampersand sum sub I in there, as I'd said before, you'll actually make sure that this addition statement is only executed by the thread that owns that element. Jim. That's right. So thread 1 will own the first 100, thread 2 will own the second, or thread 0 will own the first 100, and so on. Thank you. OK, so layouts are a little bit more general than just being able to leave them out, which we've seen. That gives you a cyclic layout. You can get a blocked layout, which gives you the maximum block size that fits within the size of the total size of the array. So basically, you just divide the size of the array by threads, and then do the right thing with the last block maybe a little bit smaller than the others. And you can also use what's called an indefinite layout. So this one may be a little bit harder to think about, but the way I think about it is go back to that cartoon with the yellow blocks. What it means is that the entire array is going to live inside of one of those pieces, one of those partitions of the address space. So when you keep doing plus plus, or you're going through your array with different values of I, they're always going to stay on the same thread. This is very useful, right? It means you can allocate a block of memory, an array in C, which is in the shared part of the address space. But when you access it, it doesn't go to the other parts of the address space. So you want both kinds, but these are very important if you want to build large blocks, large data structures that are shared, but they're not spread out. And you can actually put in multiple block sizes. So you could put in a particular block size B. So if you made B 4, then the first 4 elements would be on thread 0, the second 4 would be on thread 1, and so on. Or you can actually have a multidimensional blocking factor, which is really equivalent in C to just multiplying all these blocking factors together and giving you that particular block size. This is where the fact that C doesn't really have true multidimensional arrays kind of shows through. So you can get something that sort of looks like a blocked multidimensional array. As you'll see when we talk about dense linear algebra, these can be pretty useful. You saw it already, I guess, in homework 1. But But in this case, it can be, you'll find that sometimes you can't do, a real multidimensional array becomes a little bit harder to express than you might like. Okay, so, and the affinity of the array then is defined in terms of its block size, which is a compile time constant, and the total number of threads, which may or may not be a compile time constant, depending on how you built the program. And each element, it has just kind of the obvious affinity, which is I divided by the block size modulo the number of threads. Okay, and so, and that's true even when you have multidimensional arrays. The way to think about it is flatten your array out into its kind of the way it would be stored in memory if you just had a single serial program, and then divide it into chunks that are equal to block size pieces. So you can get sort of what we'll often see is that you'd like in a multidimensional array setting to be able to say, well, this array is laid out by rows, or this array is blocked by columns. So each thread will own a particular, like one row or one column of the array. So C arrays are laid out in row major order. So if you say that you've got an n by m array, and you say that it's got a block size of m, each one of the threads is going to get a different row. If n is greater than p, then they'll wrap around, and each thread will get a set of rows, and the rows will be mapped out cyclically. If you instead say that you've got an n by m array, and you want to have a blocking factor of k times m, that says that each one of them will get a block of k rows. And so you can do some other interesting things in here in terms of getting multidimensional arrays to get kind of more interesting kind of multidimensional arrays if you have higher dimensional arrays. Okay, now, one of the things that is in the spirit of C programs is that you can basically take any variable and ask for its address. And that includes an array element that you can ask for the address of an array element. And so you can have pointers that point into the middle of arrays. This is not true in all languages. A lot of languages, you can only point to the beginning of the array, and then you can use an index to get into the other elements. But in C, this is not an unusual programming style to have an array in which you're accessing the elements by pointer. And so you say star P1, and P1 is something that moves through that array pointing to different elements. And so you can do that still in UPC, and the same style, and it tells you something a little bit about what has to happen in the implementation of UPC. But here's our declaration. We've got a way to read this is P1 and P2 are pointers to shared integers. So these are integers that live in the shared address space. So the array lives in the shared address space, and these are pointers that live in the private address space. So P1 and P2 are private. There's a copy of those on each thread, so they could all have different values on different threads, but they're going to point to something in the shared address space. So let's see. So we've got these vectors that we've declared at the top of the program. So P1 and P2 are just initialized to start to the beginning, and then you can say things like P1++ and P2++, and that'll move them through the array. And then we can add them up here by doing pointer dereferencing rather than array indexing. Common question in C programs is which one's faster? I don't know. Did anybody play with that in homework 1 to see whether array indexing or pointer dereferencing was faster? No. But some compilers will do better things with one than the other, and that's true in UPC as well. Okay, so we've seen now we've got these funny labels, these annotations that we're putting on our variables in C. There are other kinds of annotations you can put in C, such as const and so on. But these can be, I would say, you have to think a little bit about where these go in the declaration and what they mean for different points in the declaration. So here is a little grid of the different kinds of pointers that we can have. And first of all, it's useful to think, there's two different questions. One of the questions is, where does the thing live? Does it live in the private space, or does it live in the shared space? That's it. Does it live in the white region that was at the bottom, or the yellow region that was at the top? And the other question is, where does it point? Does it point to something local? That means it points to something that's in my own little threads partition. Whether it's private or pointed to something in the shared space, it's going to be in the local piece of it. So that's why I say local rather than private. Or does it point to something that's shared, which says it can be anywhere, and it has to be somewhere in the yellow part in the shared space. It can't be in the private part at that point, but it can be. It will be a pointer to shared. So terminology is a little confusing. In some of the other PGAS language, we use the word global pointer to refer to something that can point anywhere in the address space outside of your own threads part of the address space. In UPC, we call it a pointer to shared. So we try to not separate that, just call it a pointer to shared is the term for anything that can point out into the shared address space. So an int star p1 is a pointer to an int, and that's a private pointer to an int because the default is private, so this is going to be something that just sits down in the white part of the address space. A pointer to a shared int is a private pointer, so there's a pointer that's sitting in the white part of the address space that points up into the yellow part. There's a pointer to there's a shared pointer to local memory, so this is something sitting up in the yellow shared part that points downward into the private part. Not usually a very useful thing to do, because if any other thread can see that shared variable and tries to dereference it, it can't get to the thing. So you usually don't write things like that, but it is legal as a declaration. And here's a shared pointer to shared space. This would be very common if you're doing something like a linked list representation. The next pointers would be this kind of a shared pointer to a shared thing. It would probably not be an int. It would be a struct or something, but that would be what you would get. And there's just the picture of what you get for all the different scenarios. And you get the all of the different declarations there. So there's the linked list example for the last one. Questions? Okay. So common uses of these. So int star p. They're still really important not to turn all of your variables in a UPC program into a shared variable, because they will run a little bit more slowly. So you still use these a lot when you're just building up local data structures and so on. If you have something that's a pointer to shared, that's something you're going to use to refer to remote data, and whereas one of these shared things is used to build shared data structures that are themselves linked together with other shared pointers. So in terms of the implementation, just to give you a little sense of this and where the overhead comes from, a pointer is represented in a lot of the compilers by a regular, a virtual address, a thread ID, and then something called the phase. Phase is a little bit confusing. That's because in UPC you can pick up a pointer and you can say ++ on it. The question is, is that the next element on my current thread, or is that the next element on the next thread over? Well, the compiler knows how big the blocks are, but it doesn't know where that pointer sits relative to the end of the block. So the phase basically has to keep track of where it is relative to the block. You don't actually need to know the details of how these are implemented. What you do need to know is that manipulating a pointer to shared, one of those things that's got a shared in it, is going to be a little bit more expensive than manipulating a regular old pointer. And dereferencing it, even if it points locally, is more expensive than dereferencing a regular pointer. If you're dereferencing it and it's remote, it's very expensive, but then you probably don't care that it had a little bit more overhead to take apart the pointer. Okay, so there's some other functions you can use to get things like the size of various, the thread ID out, which I had mentioned when we talked about the UPC for all. The phase, which tells you, as I said, kind of how far that particular pointer is through the current block, and then to reset the phase back to the beginning of the block. And now more useful is to understand dynamic memory allocation in UPC. So C programs are most of the interesting data structures in a C program are not things that are statically allocated. They're allocated with malloc, which is something that lives in what we call the heap part of the data structure. That heap is going to be, we can have one that's in the private space, but we can also have one in the shared space. And we're going to do that by using a different kind of a malloc call to make sure that the thing gets put up in the shared space. The functions that you use to build those kind of shared dynamically allocated data structures can be collective, called by all the threads together, or not collective. And so we'll see different versions of them. So there's the signature of UPC global alloc. Says put something up in, give me something that's in the global space, the shared space, if you will, and it can be blocked. So there's something that's a number of blocks and the byte sizes, and this is a non-collective call. So one thread can do this. It's actually a little tricky for some of the machines to implement, because you're now going and allocating memory potentially on other nodes in the system. And in this case, the calling thread then gets a contiguous chunk of memory, but it's in the shared address space, which is chopped up by n bytes. And so that would be kind of the shape of the thing that you would get back from it. And only one thread gets a pointer back from it. So a very common thing to do is a UPC all alloc, where you all allocate something together. It's going to also be spread out over all the threads, but you all get a pointer back together. Not only do you all get a pointer, which can be convenient for building up other distributed data structures, but it actually helps the implementation a little bit, because the implementation now knows when you call all alloc that all the threads are working on the alloc, and they can all kind of locally allocate their parts and then exchange information, rather than having one thread try to go up and ask the others to do allocations for them. You can do a UPC free then, which frees up the space that you've dynamically allocated. So in our experience in writing UPC applications for a number of different scientific problems, as well as kind of more graph type of problems, we typically make very minimal use of the distributed array constructs, except to build kind of the skeleton at the top. And instead, we build our data structures, link them together with shared pointers to shared, these kind of wide pointers that can be used to point to things across the system. So here's a very common kind of structure, which we call a directory structure, that would build a data structure like this. And in this case, we've got the first thing we have is a array, which is in the shared space. It's a cyclically mapped array. So I'm trying to draw the original partitioned global address space here. So this is just the shared part of the global address space. Actually, that might be sitting in the private part of the address space. Ignore the color here. But anyway, the partitions are hard to draw on this slide, so they kind of go around the corner here. So what happens is there's a cyclically mapped array, and that's right, it is a shared array. And each one of the elements lives on a different thread, and it's allocated to have a size threads right there. And that's this thing. And then we want to allocate a chunk of memory, which gets put into each memory location. So there's a UPC alloc. In fact, I think I didn't actually give you the signature of UPC alloc. UPC alloc will allocate something that's in the shared space, but it's just one thread calling it, and it's just allocating one block of memory, not a big thing that is not something that's spread out over the other memories. So you get something like this, where this block lives on thread 0, this on thread 1, this on thread 2, and so on, after that allocation statement. So these are more general. These don't all have to be the same size. And because in C, one of the nice things about C and the multidimensional arrays and so on is you can allocate something as a big flat chunk of memory, but then you can build another pointer that has a different shape, like a 3D array, and point it to that thing, and it'll work just fine. So you can a common data structure would be, let's say that we have a 3D array. And we'll put a little kind of skeleton of that array on every thread. And then every thread will have a pointer that points to the chunk of data that is owned by every other thread in the system. So you've replicated a little bit of the data of the state of the data structure, and then used global pointers to build the other, to hold most of the data. This is a very common style in UPC programs, especially for multidimensional array-based programs. It's useful because the skeleton doesn't have to have exactly one element per thread. It can have multiple elements per thread. You can have an adaptive sort of problem where there's different block sizes on different processors. So it's a very general sort of data structure representation. You need to use the dynamic memory allocation for that. Okay. So let's see, a little bit about kind of the underlying, so the details of the semantics of UPC. And you will see these in writing UPC programs, but for the most part, as I talked about when I talked about memory consistency on shared memory architectures, it's something you don't have to worry about very much if you don't want to. What you have to then do is never write a program with race conditions. If you never write a program with race conditions, you'll be fine, and you don't really need to worry about the memory consistency model. The memory consistency model in UPC, there's kind of two different modes, if you will. It can be strict, in which case any execution, any statement, memory operations executed by one thread will always appear to happen in order by all the other threads in the system. So that's the strict order. A relaxed order is I see my own operations happening in order, but other people may see them happening out of order. So that would be a relaxed memory consistency model. So you can get a relaxed model by just, in the whole program, by just using UPC relaxed. Relaxed tends to be faster than strict because strict is going to force you. Imagine that on a large-scale machine. Remember, we don't cache remote data, and there's no cache coherence. And I have multiple updates to the same remote value. Well, those are going to go across the network every time. And in a strict case, because you want to make sure if you've got different accesses going across the network that they happen in order, you actually wait for each one to come back. And so That's why you typically want to use relaxed accesses, but you have to be a little bit careful that other programs can see your reads and writes happening out of order until you hit synchronization points. So as long as you're not writing to the same variables and you've got barriers in between your regions before you're going to look at those variables, you'll be fine. There is also something to just kind of force the memory consistency model. If you don't want to have a global barrier, it's called a UPC fence, and that says it forces a synchronization point in my thread's execution such that everything I've executed before that is now visible to all the other threads in the system. Okay, so a little bit about performance. In order to get high performance out of any one of these languages, you need to get parallelism. You need to be able to scale with a number of processors. You need to be able to get good serial single node performance and be able to call highly optimized libraries like the library that we were comparing you to for homework 1, the AMD library, and you need to so there's other kinds of libraries you might want to call, or you might want to write your own highly optimized code, which would just be pure C code or pure Fortran code. So it's possible to mix languages together like that. You can certainly call C because it is just UPC, and it should perform just like C inside of any kind of a UPC application, but you can also call it to other languages. You also want to make sure you avoid unnecessary communication costs, and so you want to avoid paying for things like both the latency costs and the bandwidth costs. Now, the Berkeley implementation and the Intrepid GCC UPC implementation and the Cray implementation that runs on Franklin, but not the one that runs on Hopper, which is what you'll be using for the homework assignment, are all based on a communication layer called GasNet. So let's talk a little bit about the communication of GasNet also in order to understand what you should expect to see in terms of the performance. So one of the other things you want to do to avoid performance, to get good performance, is to avoid unnecessary synchronization or dependencies in the code. So things like avoid having load imbalance problems that cause one processor to slow down waiting for the others. All right, so the GasNet communication layer and the kind of the UPC, the PGAS model in general, as I said, although there are messages going across the network, it is not like a message passing model similar to MPI because there's no receive operation associated with each send. Instead of having send and receive, the basic operations in a PGAS language are put and get, which are the kind of distributed memory versions of load and store. So why are they different? Well, a one-sided put operation, for example, looks like this. It's got an address and it's got some data. It goes across the network, and the network interface on most machines, including, say, an InfiniBand network, not an Ethernet network, but if you've got on the Cray networks or IBM supercomputer networks, but also things like InfiniBand clusters or MirrorNet clusters, will come over here into the network interface, and because it's got an address in there and there's hardware in the network interface called RDMA hardware, it'll take that data and write it directly into memory. So it doesn't have to get any information from the CPU. It doesn't have to get any information from the application program running on the other side because everything is encoded in that address. In contrast, if you look at what happens with an MPI message, it's got a bunch of stuff in it, but one of them is a message ID. A message ID is something that's understood by the MPI implementation so that it can match the messages together, and there will be matching sends and receives, and that is going to have to be matched by some code that's coming from the host CPU because it's the user's application that controls the information about where is the buffer that this data goes into. Well, the data goes into the buffer that's in the receive message, the receive operation that matches this message ID, and there can be tags and stuff like that too. But fundamentally, I have to get information from the host CPU. Now, if you use iReceive, you're a good MPI programmer who's well optimized MPI code, you'll pre-post your receives, so you'll do your iReceives well before you expect the data to come in. That basically sets up the relationship between the message ID and the buffer, and when the message comes in, it can somehow look that up and put the data into memory. But it has to usually go up to the host processor in order to figure out what that matching is, because it's something that's it's not downloaded into the network interface except on a couple machines. So that's the basic difference between them. And so one way of thinking about this is it's harder to write programs with race conditions in a two-sided model because you have the send and receive. And it's a little bit easier in one-sided model because you can kind of do unconstrained communication. So whether that's a good thing or a bad thing depends on what kind of application you're writing, how important it is to you to be able to do things like a random read or a random write into memory versus how much you're worried about kind of controlling who's communicating what at any given point in time. So the one-sided model can also have performance advantages. These do vary across the different network implementations. This is some data taken from InfiniBand. It's a common network used in clusters. And this is the what's called the flood test. So this is a benchmark in which we're pushing data out into the network as fast as possible with different sized messages. And eventually, and either of the communication layers, whether it's GasNet used in UPC or MPI, will hit the same peak number. They should always hit the same peak number, which they do out here for large messages. But there's a significant range in here up to the small to medium-sized messages, and this shows the relative speed of GasNet over MPI, in which there's a performance advantage to GasNet. So you'll see this advantage if you're doing lots of communication of small to medium-sized messages, and you're overlapping them in the sense that you're doing put, or UPC references that are doing write operations or read operations through the network, and you're not waiting in between each one. So you need to be in relaxed mode, so they're all getting pipelined one after the other, and then you'll get better performance. So it wasn't just on InfiniBand. We've seen this kind of performance different across other machines. This is a latency graph, so down is good. So this is MPI, and this is GasNet. And so all these bars, the GasNet bar is somewhat lower than the MPI bar. Those numbers may not seem very significant, but when you're doing a reduction across a very large machine, these latency numbers do start to add up. So you do care sometimes about factor of 50% to 100% speed up in terms of the time it takes to do a reduction. If you're sending very large messages, you should, as I said, see the same performance. These are 2 megabyte messages, and this is bandwidth, so up is good. And here, this is a problem on the InfiniBand implementation that they never were quite able to saturate the peak bandwidth because of a bug in the Mellanox hardware there was a workaround for. But in general, you should see about the same performance for large messages. For smaller, kind of medium-sized messages, then bandwidth, this is flood bandwidth, so kind of injection rate of the messages as well as retiring them. For 4 kilobyte messages, you see a more significant gap. And on the Hopper machine, so these are just results from last week, and I think that they are not completely final numbers. In fact, different versions of the compiler seem to flip these numbers around a little bit, but we have done some measurements on that. So this is latency, so once again, down is good, and the UPC number is down here, whereas the MPI number is up here, and you can't really see it, but because there's a white line in between those two, which is the MPI number for what are called large pages. So there's a way of controlling the page size, which gives you better better communication bandwidth. So this is still a work in progress, though. These numbers are going to change over time. And here's the bandwidth numbers. These are now not flood bandwidth. These are ping-pong bandwidth, where you're going back and forth with each large message. So you're actually waiting for the round trip of the message. And here's the UPC bandwidth, which is higher up until a point where something weird happens in the UPC implementation. It's kind of multiple weird things happening in the MPI implementation, but that's what you see. Okay, so does this ever matter in practice when you want to be able to send lots of messages into the network? And the answer is yes. Jim will talk, I think, in a couple weeks about an FFT and how you parallelize FFTs. But without going into the details, one of the things you have to do in a large FFT is transpose the matrix in the middle of the computation. So imagine we're doing FFTs on a 3-dimensional array. You're going to do FFTs in each of the 3 dimensions. So let's say you've laid it out by planes, and each one of the threads will do FFTs on the columns and FFTs on the rows, and then you'll transpose things and do FFTs in the 3rd dimension after you've laid them out so that each one of those dimensions is contiguous. So here's what happens after you've done the FFTs here. Now you're ready to start doing the FFTs here. After you've done a certain set of FFTs, you can actually start communicating the data. And so you can, and if you use an algorithm like that where you send very much smaller messages and you send them more frequently, you have higher latency costs, if you will. It's not really latency, it's the overhead of communication, because you're sending more messages, but you are sending, you're getting better overlap because you're not waiting for the entire second phase of the FFTs to finish. And so what we saw in a few different machines is that you actually get better performance by doing this kind of a computation. So that's the UPC. The best UPC implementation is the yellow bar. The best MPI implementation is the red bar. And the UPC one is actually, in this particular case, using very small messages, which are single-row messages, which give you the best overlap. On some of the current machines, we're finding that you can't use what we call the pencil algorithm. You're waiting for a chunk of things that are contiguous in one plane to send that. And oops, there's some blue gene numbers, which also show there's the MPI implementation and the UPC implementation. So there are cases, but I have to say there's a lot of work that went into optimizing these programs, and hopefully those optimizations have been put into the MPI programs as well, but your mileage may vary. So, and the last thing, let's see, I think I'll just say we've done some work on LU factorization and others. Let me just end by kind of suggesting some class project ideas related to UPC if you're interested in it. First of all, you can do an application project. There's a Delaunay mesh generation code that was written by a previous student. So this is a very irregular sort of problem where you're trying to generate an unstructured mesh, and it has interesting synchronization problems. There's a kind of adaptive mesh refinement version of a fluid dynamics program. I say kind of because it's not really very adaptive. It's what's called a multi-block code, but it's not really fully adaptive. There's the dense LU and a sparse Cholesky implementation that I've done before. You can do various experiments with the different kinds of multi-core implementations, and we've done some of that as well. We've actually done some work on a standalone load balancer for UPC, and there's also some benchmarking and tuning work for SMPs. And I think actually probably one of the interesting areas that we're looking at now is extending the global address space idea to GPUs. So if that's something that you're interested in, we could talk about that as well. So I will just end. There's my heart simulation. This is actually done in titanium, not in UPC. But there's a couple of pointers to the web pages that if you want more information about UPC. So, any questions? Okay. Thanks very much. We'll see you next time.